Right. So we are continuing on the class on diversity. If you remember, we had started off with we had already had two classes on diversity, and initially we started with the wired communication and the aspect of wired communication in getting a very low bit error rate. And further we extended our discussion to how in wireless communication we are actually offering a much poorer VR condition, given the fact that we know the signal to noise ratio of the end user. Mhm. Right. So in that way, we observe that in wireless communication, the major problem or the bottleneck is that we don't have a very high bit error rate, but we want to achieve that because we want to have wireless scenario for most of the communication. And keeping that in mind, we found out that the reason for the wireless communication for providing such a poor VER was primarily due to something called as the multipath effect, or we consider it to be the deep fading condition. If you remember, we had done that deep fading condition as well. And we have observed the BER, which was just a generic function of SNR in the previous case. For the fading scenario, it becomes something like A square into SNR, where A becomes the magnitude or the amplitude of the nature of the multipath that we are taking into account. And as that A part that we are looking at over there is completely random in nature, we wanted to find out something called as average BER, and we found out the average BER can be derived to be something like half of square root of 1 minus square root SNR by 2 plus SNR. And this happens to be a very key element because we somehow found out that the nature, the reason for such a poor BER performance, and we have to find out a solution out of it. So in order to do that, we found out that there is a way of tackling this particular scenario, and that is where we discussed about something called as the deep fading scenario, and we discussed about something called as deep fading. That is the main reason the randomness of this analysis is coming in. And by deep fading, we mean is that when there exists only a single path between or a link between a user, transmitter, and the receiver, there is always a high chance that there will be a scenario where the communication will cease to exist. And in that case, there will be a high chance of VR, provided that in transmitter we are sending one, and in the receiver we are sending receiving zero or nothing at all. So in that way, the deep fading, the probability of deep fading, the more it is, ideally we would observe that we can see here, in fact, that the probability of deep fading is almost proportional to generating a very high bit error rate as well. All right. And this, in fact, if you observe that PDF, which we have like probability of deep fading, that is also directly inversely proportional to the SNR being used. That means when the channel condition is relatively good, the chances of having a deep fading will be less compared to when the channel SNR is very high. That is, the channel is in a good condition, you can say in that way. The probability will be definitely low. So in that way, we observe that diversity can be one such technique which can be used to a certain extent to eliminate this effect of deep fading, keeping in mind that there will be multiple existing elements or multiple paths that might exist between the transmitter and the receiver, and that will eventually mean that even if there are some paths which might undergo a deep fade, there will exist some kind of existing path which will make sure that the communication still takes place between a transmitter and the receiver. And that will eventually make that even if there is a deep fade, there is a probability of deep fading is very high also. But in that case also, we are going to get almost relatively better performance compared to the uh, single channel communication or a CISO communication. This is the time when we started to discuss about the receiver diversity as well. And if you remember that I told you the transmitter diversity and receiver diversity, which happens to be something like this. This is basically a receiver diversity where we are including two set of antennas at the receiver, and we are experiencing two set of links, L1 and L2, which happens to be carrying the same information which is transmitted over from T1 or transmitter. And that means that even if L1 fails, L2 will still exist, and hence the bit error rate will be definitely going to come down. And also in the process of this diversity, what we have observed over the period of time with the derivations and all, we observe that with this scenario in mind, there are certain techniques or some algorithms which can be imposed on top of it in selecting the cumulative outcome of this receiving element. And that is where we discuss about two of the elements, which is called as MRC or equal gain combiner. One was MRC, which we had discussed on last day's class itself, which is called maximal ratio combining. And the other one is equal gain combining, which we are going to discuss today. In fact, these two techniques we are going to test in our lab as well. We are going to do an experiment on that as well, so that we can get a very good knowledge about these two. Why we are doing this and we are not doing the others? For example, there are two others methods also, like selection diversity. There is something called as feedback diversity. There is something called as some few more techniques as well. But selection and diversity or the feedback diversity will never give us the similar performance as that of MRC or EGC. In fact, MRC is the maximum throughput. That gives you the best outcome. But the problem with MRC is that the implementation time, there are certain hazards or complexity associated with it. I'll tell you that. So that is sort of taken care of while we do the equal gain combiner. There are certain advantages of equal gain combiner, but equal gain combiner will definitely reduce the efficiency of the system. It is not comparable to MRC. It is comparable to MRC in the sense like it will give you very closed approximated value to that of MRC, but it won't supersede it. That is what the thing is. But as far the implementation is concerned, it is relatively easier. There's a reason for it. We'll tell you that today. So keeping that in mind for MRC, so what exactly MRC did was something of this nature. I think I already had shown you one diagram. If I'm not wrong, it is not here. I think this diagram only I have drawn on last day's class, if you remember. So this was basically what MRC is doing over here. So ideally, you can understand that we have a transmitter and we have the two paths, as you can already have seen over the period. Now we have N and N1 or N1 N2 in basically the AWG noise, which is fairly okay. And we have the signals Y1 and Y2 coming in out of it. Now generally, if you say that diversity, if it is, the diversity is actually achieved by these two paths. But to improve the diversity, we will need these combining techniques. So that is where if you observe that we are using a certain element somewhere over here and a certain element somewhere over here. Alright. So the portion of H, H prime or H bar divided by norm of H, this symbol is called as norm of H. Normal value, we will take it usually. So norm of H, H is a vector quantity. So H bar divided by H norm. And where H stands for the multipath coefficients for that matter. If you take that as a weighting factor, then accordingly based on the weightage of H and H prime, individually there will be a combiner that will take place. As you can see, this is where the combining signal is getting in. So that's why we call it the combiner. In equal gain combining also you will find a similar kind of diagram, except that the weighting condition will change. That H prime, H bar by the mod of H instead of that, or the norm of H, we will take something else. But in MRC, the main objective of this combining technique is that whenever we have two paths or more than two paths for that matter, we have to make sure that whichever has the maximum throughput, we should select that particular path. That's all. Okay, so that is the main objective. Now, if suppose somewhere which is very low, but I need to boost it up, so then this weight factor will try to boost the signal to the maximum strength. Similarly, if the signal is very high, then maybe the weight factor will try to reduce it so that there is a normalized outcome that we are getting. So that is basically a balancing act that these weight factors are going to do. Now, how do we select this weight factor is depending on whether we are selecting a maximal ratio combining or we are choosing an equal gain combining. That's all. So the weight factor or the portion that I have circled over there, that is ideally used to find out a kind of an optimal solution to the combined effect. Okay? So keeping that in mind, if you remember on last day's class itself, we had derived to certain extent, we have derived to a very important relationship over in this diagram. And I told you that one of the most important factor over here is this equation where we are looking at SNR max, which is we are talking about the maximum SNR that we are going to get, because that is basically the sole objective. We want to make sure the SNR is very high, because if SNR is very high, then the probability of deep fading is relatively low. Now, as we have already established, if the probability of deep fading is low, definitely my BER will rise up. So that is basically the link up to it. So if I can increase the SNR is directly inversely proportional to PDF. If you see last, I have seen. So if I increase the SNR, definitely the PDF or the probability of deep fade will come down. But again, probability of deep fade is proportional to BER. Hence, the probability of deep fade if comes down, the BER will proportionately come down. So that is basically the objective. So keeping that in mind, we found out that SNR max can be given by a relationship P by sigma square normalize H square, and in that part of it also you can see that we have mentioned that which is a part of, this is how we calculate. So if there are two parts or two of the if there are two set of paths which happens to have coefficients h1 and h2, we will have h1 square and h2 square absolute values of it, and that will be considered as to be the values. Right now, if usually we consider it as a general case, then definitely this needs to be extended to L number of paths. All right, so we'll see that today itself what exactly it is. But prior to giving that, this is where we ended almost our discussion, I guess, where I have given you the expression for what will be the weight factor if we consider it that way. So we have found out that for the MRC, this is very important because we will see the equal gain combiner as of today. So you can understand this is basically the equation. Very important is the factor which we are looking at over here. So this part you can see, this is a vector part divided by the norm of it, and in representation wise, this is how we represent. Right? So this is where we end, and we did some question on that. We had found out that if I get a question on this nature, where we have H1 and H2 provided to us, when we have an H2, H1, H2, which are basically the coefficients of the channel, we have observed that we can find out what is my SNR compared to when given an SNR of 10 dB. For SNR MRC, we are getting around 13 dB. So it isn't boosting up by 3 dB, only by two set of antennas for the similar scenario. All right. So this is how it is. This, in fact, we are going to prove even in lab as well. We are going to prove that in lab as well as an assignment later. All right. Now, keeping that in mind, let us try to prove the generic equation for MRC. So please make a note of this. This might be useful at later stage for you. So this is basically where we are looking at the general MRC. That is when we have the order of our antennas or diversity order. We call it the diversity order to be of L. L means here, you can see over here, we have mentioned as L antenna system. We have mentioned as L antenna system. So L antenna system means now in this our example, most of the time we are taking two antennas for that matter. But it can be extended beyond, but you will soon observe that after a certain period, if we go on beyond two antennas, manually the calculation becomes very, very tedious. So that's why for most of our generic theoretical study, for our research work also in terms, we will try to consider only two antennas at the receiver. Alright. So, but in general, what will happen, it will repeat for the L type of antennas. So you can see that if there are L antennas, then this factor of H, okay, so it will be like H1 square plus H2 square plus up to HL square. And if I represent that by a factor of G, now naturally this G is also a random factor. Because remember H1, H2, H3, these are all random itself. Alright. So if this is G and this G has this, you don't need to learn as such, but please make a note of it. You won't be using it as such. This is called as the chi-square distribution. This is when we are when the factor is a random factor, G is a random factor, which depends on another random variable. Then we usually represent it in this order. We don't need that. It's just an expression for the time being, but it has a meaning later on. Okay, we'll see that. So what we're trying to achieve is, you can see this is the distribution of the factor G, which is composed of H1, H2 up to HL. Now, if I consider the equation that we know, SNR max, which is H square log H square P by sigma square, so we can replace this whole thing into something called as G by P by sigma square, and we know the P by sigma square is nothing but SNR. So if you observe that we are trying to get a hold of something which looks very similar. Can you see this? SNR FD, we found out little while back itself, it was S square SNR, something like this we have derived a little while back. So same thing is we are trying to do. Here instead of the S square, we are writing it as G. When we discussed the A square part, that was only for a generic discussion for wireless scenario. Alright, that is where we discussed that A factor is a random. Now, after MRC is done, now we are trying to evaluate the same thing, and we come across something called as a GSNR over here. And if you remember this equation as well, we had already established long back that VR is nothing but Q function of square root SNR. So instead of the SNR, we are just fitting in the value of GSNR. Alright, but as you can understand, SNR, although it is a constant, it's a factor which is not random as such, but G is a random factor, and that depends on the chi-square distribution. The final expression, this is very crucial, please make a note of it. The final expression for MRC, the average bit error rate, please make a note of this. I'll explain you by a question on this. The average bit error rate for an MRC, this is for MRC. Okay, the general expression for average MRC is given by the expression given over here. 1 minus lambda to the power L divided by 2, where lambda is given by square root SNR by 2 plus SNR. SNR by square root 2 plus SNR we have already found out. Remember, in wireless communication we have also found out. When we discussed the BR for wireless scenario, we had come across this term. So we are just representing that term over here. Summation of L equals to 0 to L minus 1, which indicates the for loop, you can say it that way, which goes from first antenna, the 0th antenna, to the L minus 1th antenna. So like that we can say, or if it is 1, then it would be L. Then we have a function, this is the NCR, that's why I have mentioned over here. This is nothing but a combination that we know. NCK, so that's the text even. So capital L plus L minus 1, CL multiplied by 1 plus delta delta by or delta or gamma by 2 whole to the power L. So this part of it, if you observe, it is a very little difficult at times to evaluate. We'll see that with the question also if time permits. But at this, for the time being, you write, because this is a general equation. This is a general equation for average BR. The problem is not with L equals to 2. With L equals to 2, which is we are doing, L equals to 2 means 2 antennas at the receiver. Remember, that is where we started off. L equals to 2, it is fine. But once you go beyond that, when you go to L equals to 3 or even L equals to 4, the equation of solving this kind of an equation becomes a real trouble. Manually, it is very difficult and tedious process to do. So in order to do that, we will take an approximate solution of it. So please make a note of it. It is not mentioned in this note, but the one that I'll upload, it will have it and we'll solve it accordingly. So please make a note that this whole box that you are looking at can be approximated to 2L minus 1 CL multiplied by 1 by SNR, 1 by 2 SNR whole to the power L. Please make a note of this. This is missing in the document, but the one that I'll upload, it will be there. So this whole box that you're looking at, we are not going to invest much on this, except that if L is more than 2, we are going to evaluate it using the equation given over. We can even use the L equals to 2 equation for this also. We don't have any problem. We can use that. But as this is a generic equation, the below statement, we will have some equations, like a problem or solution on how to solve this kind of question with the basic equation. But in terms of its mathematical part, or when the question might come in for your examination purpose, we are going to approximate this whole box equation to the one that is given at the right side. That is basically a closed form expression of this whole segment. It is very difficult to prove as such and even understand at times in different parts. We don't need that. It is just that the last part, 2L minus 1 CL given 1 minus 1 by 2 SNR whole to the power L. Please make a note of this. Alright. So in your exam, if at all it is explicitly mentioned, you can try out with the right hand side. If it is explicitly mentioned to use the general equation, then only you are going to use it. Otherwise, you can take the approximated equation because that will be much easier for you to solve. All right, where L stands for the number of antennas. Okay, so keeping that in mind, this is all clear, right? This is a very important equation for you. Please make a note of this. All right, so this is the average BR, because again, remember what we are trying to achieve. We are trying to achieve a low bit error rate given that we have high number of antennas, whether we are achieving that or not. So keeping that in mind, this particular question, this is just an example of it, that if I have N equals to 2 and we get the general equation, when we substitute all together one by one over here, we go on solving it this order. You can see this is how we have solved the first part, because you can see here it is L equal to 0 to 2 minus 1, because 2 is L equals to 2 at this point. So it is L minus 1, so 2 minus 1, and it is basically how the distribution is going on. And if you see over here, when we go on calculating it accordingly, we are getting at SNR 20 dB. We are getting an SN, suppose SNR 20 dB is provided to us, then the average bit error rate is coming around 7.25 into 10 to the power minus 12. So the objective over here is, the calculation part is, you can look at it later also. There's not much difficult that is, as it is. This is just a combination of the two cell elements that we are calculating, and we are substituting in the basic equation. And after solving everything, where the gamma is given by square root SNR by 2 SNR, we get a value. Remember, linear scale. I told you multiple times that you please convert that to linear scale. And if you do this, we are getting a value of 7.2 into 10 to the power minus 5. Now, if you remember, when we started our discussion on diversity, or before that, I told you that for wired or wireless scenario, 10 to the power minus 6 happens to be a standard set of error or bit error rate standard. We usually consider that to be a standard bit error rate. So you can see it is coming out to be a very low bit error rate. 10 to the power minus 5, very insignificant bit error rate. Considering this is a wireless scenario, considering there is multipath that is going to happen, considering that there is a deep fading chance that might happen. So every worst possible scenarios we have included in our discussion. But even in that, we are achieving a bit error rate which is almost equivalent to a wired scenario. Understand the significance of the diversity and MRC. So that is basically the objective that we started off with, that we have improved the SNR improvement, and in the process we have made sure the probability of deep fading has come down, and that is resulting into an average bit error rate which is also substantially very low, and it is comparable to almost the wired scenario. So we are getting all the benefits of a wireless scenario, wireless communication, but we are getting a very poor or very low value of bit error rate, which means that the efficiency of the system is very high. Is it fine? This is a very nice observation actually. So if you do the same question you can do the same question using the formula 2L minus 1 CL 1 by 2 SNR also, where SNR is 20 dB and L equals to 2. You can get a very similar result, but it will be approximated. But you will find that the order of the bit error rate will come around the 10 to the power minus 5 mark only. As I said, the magnitude here is not that important. It's about the portion of the 10 to the power minus 5 or minus 2 that is important. So we are attending almost minus 6, almost a very low value. So that is being given over here. So you can see which is significantly reduced compared to a no diversity scenario. What is a no diversity scenario? It's a CISO scenario where L equals to 1. We have single antenna and single receiver. So there is a high chance of the deep fading. So if you check in page 4 of this document, we had derived a non-diversity of 4.92 into 10 to the power minus 3. We had derived that earlier. So this was there when there was only single antenna. So using two set of antenna with the similar patterns with an MRC technique, we are getting a 7.2 into 10 to the power minus 5. So it's a drastic improvement in the bit error rate. Right? So that is basically the advantage of having a diversity, and for that matter, that is the advantage of having an MRC which is giving us this result. Clear idea? This is about the MRC altogether. Okay. Now, as we have discussed about the MRC and we have understood that MRC is nothing but an algorithm that picks and chooses this weight factor, the optimal weight that needs to be used. Now, let us see the significant part of the equal gain combined. If you see the diagram, it is absolutely similar to that of MRC. Absolutely similar. You have the two parts, L1, L2. We have the two Y1, Y2s over there. But if you observe over here, this is where it changes. It is not a norm factor. Remember in MRC, we had a norm. we had H norm over here. But here you can see that instead of H norm, it is for individual path. It is H1 absolute value and H2 absolute value. Can you please go and check the previous diagram? If you are having it, if I happens to have that diagram with me. So this was with MRC. If you see this, this is the normalized. It is normalized over all the values of H. H is containing all the H1, H2, H3, everything. But if you see here, it is based on individual H1, H. So for individual path, it is basically trying to take care of. So what is the advantage of this? Because it is almost similar to looking like the structure of an MRC. The advantage of it is given somewhere at the down over here. So the interesting factor with EGC is that each single branch weighted with the same factor irrespective of the symbol amplitude. This is a very, very important element to it. Which means that if given the fact, I think I have already established to you that the H factor, I think if I give you the write-up over here, that H is nothing but an amplitude and a phase. So I told you long back when we were discussing about what is H. H was given by A e to the power J5. So the same thing I am writing over here. So if I can ignore the randomness of the amplitude for each and every path, and we are only focusing on the phase component of the multipath signal. So you can see here, it is mentioned over here, irrespective of the symbol amplitude. So amplitude is not taken into consideration at all. Only what is done, but they must undergo a co-phasing. Now what is co-phasing? Which means that all the received signals, all the received signals via different branches will be aligned such that system combines the maximum signal strength. So again, we are trying to achieve the maximum signal strength, but we are ignoring the effect of amplitude of individual path or the signal that is undergoing. We are only looking at the phase part of the signal. That's all. Because this makes the calculation drastically reduced. That's the main reason. Nothing more than that. And as per the implementation is concerned, this becomes relatively easier. That is the reason equal gain combiner has its role. Nothing more than that. Ideally, MRC should be giving you the best outcome. But as far the implementation is concerned, equal gain combiner is relatively easier. That's all. So although we will compromise the efficiency to a little extent, but as far the implementation is concerned, it should be easier. That's all. So if you see here what I have done, H is this, H, we are taking a conjugate of it. So H prime and H prime by the mod of it is given by the e to the power minus J5. So that's the correction that needs to be made. So for each and every path which has a phi 1, phi 2, phi 3. So all the paths of phi 1 or relative to it, they will be aligned together. All the phases with phi 2 will be aligned together. So like that, it will be forced towards the end and it will be combined together. So you can see the amplitude remains unaffected. We are not bothered with the amplitude in this case. In fact, that is the reason why it is not efficient, because we are not taking the amplitude into account. But as I said, the complexity is relatively lower here. So this is basically the factor. So if you see over here, we go on with the same type of calculation as we have done for the MRC. So we have y bar, which is given by the combined value of y1 and y2. Why? Because you can see here, y is nothing but of y1 and y2. And what is y1 and y2? y1 and y2 is nothing but the combination of y1 with this multiplication and y2 with this multiplication. So that is being done over here. So y1 into h1 star h1 absolute value of it and h2 of this and y1 and y2. What is y1 and y2? y1 and y2 is nothing but, if I go back, y1 and y2 is nothing but n1 and we have h1. So h1 x1 and x into h2. So this is being shown over here. This is basically general equation like we have done. You can see it's already mentioned over here. So we recollect that y is equal to hx plus n. So we have substituted over here, and as I said, we don't need the derivation as such, but what we are getting is very important, is that after combining everything, you are getting some very simple expression. h1 into x plus h2 into x where H1, H2 I'm saying in terms of absolute value, plus the n factor, which is a noise. Leave out the noise part because that is anyway a random Gaussian random variable, so we take care. We are not bothered much with that right now. But if you observe here, if I take common of x, so it is basically a addition of absolute values of H1 and H2. It's just that. So if I take L numbers as such, so there will be a summation of L such absolute values, just like that. And in the intentionally, like what we are getting is that the y bar is nothing but at some point it is just a summation of the absolute values of h into x plus n. And if I take the SNR condition, because we are trying to find out the SNR of EGC, please make a note of this box. SNR EGC is coming as very important summation of I equals to 1 to L, because that is basically my signal part. You can see I have mentioned over here the signal part of it. Signal to noise ratio. So the noise part is L sigma square because there are L paths. So that comes to L sigma square. If you remember, I told you one path it is P by sigma square. So sigma square is indicating for one path. But there are L paths here. So that's why L sigma square. That's mentioned over here in the detail. And the signal part is nothing but P times. P is the signal quality, as we know, for we are taking that assumption every time. And the summation is nothing but the summation of the absolute values of the multipath portion. And if I take the ratio, you can see one very interesting observation, very important observation, and that is that it is divided by something as an L. So if I leave out this L, it is nothing but summation H1 square A multiplied by SNR. But it is divided by something called as 1 by L. It is coming that way. Because L sigma square is the noise. So basically, if you increase the number of L, and if you take this assumption of it, you will get some relatively little bit lower value of SNR EGS compared to EGC compared to SNR. Because if you remember, I think I have mentioned over there as well. If you remember in SNR MRC, what was the equation? Normalized of H square into SNR. But that was not divided by any L. Alright? But here the division is by L. So that is why it is reducing it to a certain extent. We will prove that, as I said, in lab as well. This we will prove it in the lab as well. In the assignment as well. Right? So please make a note of this equation, because that is where we end up most of the discussion with. Now we dig deep into this equation a little bit to generalize this equation. So please make a note of this as well. This is very common. I have just consolidated both so that we can compare together. So maybe one thing is, I'll just reduce the font a little bit. So this is called optimal weight of MRC. WMRC, just the previous page we have mentioned that this is nothing but a weight factor. Now in case of MRC, this weight factor is nothing but H vector representation by the norm of it, of the whole channel, H and H. But here the EGC is nothing but the division of H1 by absolute value of H1. Alright, so that is the major difference. And this is relatively easier to perform because we don't need all the H. We only need that particular branch and its coefficient. That's all. Alright, so that makes the calculation to be a relatively lower, little less in that way. Alright, so these are the experiments. I have kept this as a formula because you might make the notes later on, or where you are making it, you keep this as the formulas intact. Then the searching would be easier for you to do. Now, if I go a little bit deep into the SNR equation that we have discussed right now, so let us try to generalize it. So let us all be, this is all like pretty okay as such. We just H1 square, which you are looking at over there, that can be again broken down into subsections, and the explanations are given over here that we are trying to find out the power and the cross terms, which is basically the interfering power. And after doing all these things, let us not go into detail. Please make a note of the generalized equation. So the SNR EGC, if I don't take into account the H part as such, if we try to ignore the whole element, we usually come across a scenario just like we had it for MRC. We have now here 1 plus L minus 1 into pi by 4 into SNR. So please make a note of this. So this is again in connection to the equation that we have discussed, SNRF, something like A square into SNR. So if you see this A square term, is represented in different ways In MRC, in EGC. That's all. In case of EGC, it was in case of MRC, it was represented in terms of H square or the norm of H. Here it is of this factor. Just if you take the generic approach to it. So if you know the value of L, you substitute over here, you will get a value of EGC. Alright, so this is basically SNR EGC, and accordingly, we can also find out the bit error rate as well. We can find out the bit error rate as well. So maybe I'll just give you that as well. We'll come back to this question later. So the bit error rate of EGC will be nothing but, again, 1 minus half of 1 minus square root SNR by 2 plus SNR. The same thing I have done. But if you observe carefully, this is expression that you are looking at. Please make a note of this expression. I'll tell you one very important thing over here. See this expression. Please make a note of it. Half of 1 minus SNR into SNR plus 2 by SNR plus 1. Now the interesting part is this equation only holds for L equals to 2, as you can see here I have mentioned. Alright, this is only possible, this equation is one of the equation for EGC with L equals to 2. But if you go for L equals to 3, only by 3 antenna, only one antenna if you increase and you go for the BR calculation, this becomes a hyperbolic function equation. We don't need that, and it is a very, very complex equation to remember in such for that matter. So we won't be complicating ourselves as such. So what we observe that the SNR part of SNR EGC can have a relationship with respect to the optimal weight. We have also observed an SNR with respect to the general expression, the L minus 1 pi by 4 expression. And finally, for EGC, for L equals to 2, we get an expression, a relatively simpler term, although this is not very easy to prove, but this has some references which we don't need to go ahead with. The final expression is only enough for us. So we know the value of SNR, we can substitute and we can get the final observation. Alright. So that is all with respect to EGC and their formulations with respect to SNR and with respect to EGC. Now let's take an example. Any doubt in this type of EGC? Why or what we have done over here? Maybe I'll just take one single or two question on this. So ideally, the process is to make sure the SNR improves, because with the more SNR, if we can improve, the probability of deep fading will come down. As probability of deep fading will come down, the bit error rate will go low. Alright? Because they are proportional. In order to do that, we have discussed two of the techniques. One is the maximal ratio combiner. The other one is the equal gain combiner. In case of maximal ratio combiner, we are trying to maximize the throughput with respect to amplitude and phase. And we are taking the expression, the weighted expression in terms of the norm of the whole channel. Whereas in case of EGC, we are taking individual path and we are only taking the phase component of it. We are not bothered with the amplitude of the individual multipath. And because accordingly to this, for both the cases, we have found out what are the optimal weights for MRC as well as EGC. We have observed the SNR expression for MRC, BR expression for average BR for MRC, and expression for EGC for SNR, and BR expression for EGC as well. Right? Keeping that in mind, let us try to solve one question. Okay. So please make a note of it. So for example, this is a very simple expression, simple question which we have done on last day's class also. This is just a comparison to that same question. If you go back to previous day's question, I think I have it over here. I think it is over here. So if you remember this question, we had already solved on last day's class, taking H1 as 1 by square root 2 plus H, this expression. The same question, but now in terms of EGC, we are trying to achieve. Alright. So we have given the H1s and H2s are given over here, and the SNR is given as 20 dB. The question is, find out the achievable MR with respect to MRC and compare it with the EGC in terms of achievable SNR. So how much it is relatable? That is what the question is. Now in case of MRC, if you remember, I think I will show you this. So in case of SNR, the calculation, we have come across something called as SNR is equal to 2 SNR. SNR in MRC for this particular expression, because here also there are two set of antennas. So SNR at MRC came as 2 of SNR. It came in some way. After that, we had taken some approximation. If we ignore that, So SNR MRC came as 2 of SNR. Alright, so we take that into approximation now. So you can see 2 of SNR and SNR is given as 20 dB. Convert that to linear scale, substitute. So you are getting SNR MRC is around 2 into 100, which is around 23 dB. So basically 20 dB is the channel SNR, but you are improving it to 23 dB because of the diversity scheme. Right? Now in the same order, we use the generic equation for EGC. That is how the questions usually comes in, where we compare. So SNR EGC, we have the expression, simple expression, the general expression. We substitute the respective values and you are getting around 22.56 dB. You can see there. Just a fractional change. This is 23 dB in MRC. Here it is 22.56 dB in EGC. But the major advantage is that EGC happens to, as I said, as it doesn't take into account the amplitude part of the multipath component. So that structuring or the modeling of EGC is relatively easier. Calculation wise also, it is relatively simpler. So that is why you can see that if I compare the SNR improvement, AGC is definitely lower than MRC, but by only small fraction. Alright. But if you say with respect to the best value, definitely MRC will give you the best. Okay, so this is a very simple question, simple answer to it. So in this part, I have not done over here because this is already being proved in the previous diagram for MRC. So I'm not doing that. It's nothing but taking the weight average and take the necessary approximated value. That's all. H square you have to find out by making sure that H bar by norm of H. That is what it means. And those things you can see is mentioned. Please check the question on MRC. So that when you refer it, you can go back to the MRC document and you can check it. Alright. So this is one question where we can get the answer of it. The other thing, I think one question is there. It is based on the BR. Now, right now we have explained about the BR over here. Just now we have done the expression over here. Now, suppose we have the same question over here with SNR as 20 dB. Now, when we have an SNR of 20 dB, so we substitute over there and we are getting around a error which is 1.25 into 10 to the power minus 6 for a 20 dB SNR. Now you can see as calculated before for BR MRC, what was the SNR at that time? Was it 20 dB previously? Let me just check it. Here when we did the calculation, SNR was 20 dB. SNR was 20 dB. Alright. So the same SNR we are considering over here as well. So you can see that for EGC, we are getting 1.25 into 10 to the power minus 6, at least in this particular scenario with the given channel condition. Whereas MRC has 10 to the power minus 5. So you can say EGC at this point is working much better compared to what MRC is doing at this particular point, given the channel condition is known to us and 20 dB is the SNR. Although on an average it won't happen, but this is just a specific sample we have taken. So you can see that in terms of the amplitude, ignore that. This is 10 to the power minus 5, this is 10 to the power minus 6. Alright, so the difference lies somewhere here. So it is slightly better. So although in terms of SNR improvement, MRC leads EGC, but in terms of BR, EGC slightly improves or slightly better compared to MRC. So somehow there is a compromise that needs to be made, what you want to achieve. Which one do you choose amongst the system? Alright. So this is where, as you can see, so to conclude, as per the closed form expression of BGC is slightly better compared to BR MRC, but SNR improvement MRC is slightly better than EGC technique. Right? So this is all about the portion of the module 5 where we have discussed about the diversity scheme. On Wednesday class, we'll come back and we'll solve some numericals only based on the equation that we have derived. Because the more we solve this type of question, the more it's easier. Next day when we come back, I'll just give you the statement and I want all of you to bring your calculators and all so that we can solve it over here and we can get a hands-on experience on this. The more we do it in the lab also, the concept will be more clearer. That's why the lab experiment which we are going to start from today itself, this directly will be based on the question that or the type that we have studied right now. So that we can relate. I think that will be much easier for you to do. Alright, so we'll come back next day We'll do some numerical, and if time permits, we'll extend our discussion. Sorry? Derivations won't come. Derivations won't come. Derivations won't come. The final expression or the specific equations that I told you to note down, those are important. Because based on that, you can substitute the data and you can get the result. That's all. That's all it's expected out of. Okay, no derivation, nothing. Because this derivation, as I kept on saying, these derivations are research related activities which we don't have the time and you don't have the, I would say, the background knowledge to get hold of things many places, which I don't think is required as also as of now. So we don't need to divulge into it. It's just that the derivation I have mentioned over here, because without the derivation, if I just write the equation, it doesn't make sense. Where suddenly the equation came up. So that's why I have done it. If you are interested, you can go through it because it's not that difficult as such, but it is just a mindset that we have that it is too difficult. We are not able to understand. So if you find that difficult, ignore it. Just take the final expression. But if you are interested, you can go through the steps also. That's it. Thank you.